Hello everyone. So the last three lectures in this week, we have first seen what is the driving force for diffusion. Then we saw how the phases develop in the interdiffusion zone, some of the factors that influence the phase growth, for example, temperature, time, the end members. And we also discussed how in a binary diffusion couple only a single phase region grows and so on. And in the previous lecture, then we took several examples of various types of phase diagrams that are possible between the binary systems. We draw some schematics on how to construct the composition profile given the nature of the phase diagram, given if you know how the composition is or how the phases are in the interdiffusion zone. Similarly, I also told you that in reality, actually, this we will cover when we come to the techniques of measuring the diffusion, that in reality, first we actually then we try to identify the phases based on the phase diagram information available. So nonetheless, it is a good and important exercise to understand the correlation between the phases that develop, and then how do we construct the composition profile. So today you can think of it like a practice session also, where last time we took the schematics. This time I am going to show you several examples from the real diffusion couples that are reported in the literature. Remember that some of these papers are open access, so we directly have the micrographs, but wherever it is not, I have given you the link and I have just shown the schematic. So you can actually go to the link, and if you have subscription, you can see the micrographs. So let us begin with the first example, which is a gold copper system. So gold copper both are FCC structures, quite an important system. You know that the copper additions are usually made in a very small quantity to gold to provide strength to it. So the gold copper phase diagram is something like this, which is isomorphous, and then it is also has a miscibility gap, plus some intermetallics are also forming. So now let us see, what I am going to do is now show you this profile. So you see that this is the profile obtained when a gold copper diffusion couple was annealed. Now it may have been annealed at temperature T1 or T2, but you guess that which temperature it likely corresponds to. So either T1 or T2, based on the previous lecture what we saw, what are the fundamentals of drawing this composition profile. Can you take a guess? Of course, the answer is following in few seconds, but if you can take a moment to guess whether such a composition profile would correspond to T1 or T2. So the correct answer to this would be this will correspond to T1. The reason is that at T2 you have regions where the two phases are there. So if the diffusion couple had two phase regions, that means another phase, then there would be a jump in the composition profile. Remember, it may happen that when you form a gold copper diffusion couple at T2, it may still be only giving a solid solution, but in that case you will still see a jump even in the solid solution phases, because there are ranges of composition where solid solution is not stable. So therefore this particular composition profile corresponds to T1. Now let us take another example, which is nickel tin system, and this nickel tin system is important when it comes to the electronic kind of applications. So this is the phase diagram of nickel tin. So you see that last class we saw some schematics about solid solution, about the narrow intermediate phase, about the wide intermediate phase. In reality, you have several diagrams, phase diagrams, in which you have a combination of all of these. So you have, for example, in this case, a solid solution of nickel. You have a compound Ni3SN, which is a narrow intermediate compound. You still also have a Ni3SN4, which is a relatively wider range. You have something line compounds. So all these combinations exist in reality in the actual phase diagrams. So if a nickel tin diffusion couple, so this is an example of a micrograph that is developed when the diffusion couple is annealed at 215 degrees centigrade for 168 hours. What you see here, the word SPS is just a processing technique for formation of nickel, which stands for spark plasma sintering. So when the nickel diffusion, nickel and tin diffusion couple is formed, what you see in the phase diagram is Ni3SN4 phase being developed. So if you want to refer to the original micrographs, you can refer to this paper. This also happens to be paper from our research group. So now if you want to plot a composition profile, so for the entire of this lecture, I will be, I think, putting this statement that before you proceed on with the video, you try yourself to how to sketch the composition profile. This will give you some practice of the schematic fundamentals that we learned in the last class. So if we see the answer, it would look something like this. Let us see the tin profile, which is here in the brown color, nickel is in the green color. So the thing is here, the initial region you have only nickel. So pure nickel, therefore you see the concentration of tin is 0. And then since we have only Ni3SN4 formed in this region, then you have a jump in the composition profile. So basically Ni3SN4, the atomic percent is of tin is somewhere here. So that's why you see a horizontal line here. And then the tin again, when you encounter this end member, then it is a 100% tin. So this is how the profile has developed when you anneal at 215 for 168 hours. Then an example from refractory elements, so which is tungsten zirconium. And so are you also noticing that when I am taking the binary diffusion couple, you only see single phase regions. Okay. So now tungsten zirconium, again this is a phase diagram where you have one intermetallic phase which is W2ZR, and when we form a diffusion couple at 1500 degrees centigrade, remember both of them are high melting point elements. So the phase diagram we have started from 1400 itself here. So tungsten has a very high melting point. So now when we form the diffusion couple between tungsten and zirconium, so this is an actual micrograph taken from this reference, and you see that here the phase that is developed is W2ZR. So you don't have any solid solution phases visible in this micrograph. And now the question is, you see, as I said, that although there is in the phase diagram some phase solid solution phase present, but in actual diffusion couple we don't see any. So this also again should remind you of what we discussed in the last class, that although only the single phase regions grow in the binary diffusion couple, but it is not necessary that all the single phase regions will be visible. It is completely up to the actual kinetics. So take a moment to draw the composition profile. It should look very similar to what we saw in the last example. So here if you take the tungsten side here, you see that this is zirconium. So the tungsten is 0, and then there is an increase in the or there is a jump, there is a discontinuity in this profile because you don't have anything in between. So you have a W2ZR formed, and then you have a tungsten formed. Remember one thing, how much this is developed this information is not available in the phase diagram. This is a kinetic information. So, the thickness of this is actually not, it is kinetically controlled, it is diffusion controlled. So, that information we cannot correlate with the phase diagram. Okay. So, what you can correlate with the phase diagram is whether the phase that is formed is here or not, are all the phases here or not. So, about the phase formation, you can correlate with the phase diagram whether something is there or not. But how much it will grow, whether it grows to 10 microns, 15 microns, 20 microns, that is something we cannot get any predictions from the phase diagram. So, moving ahead to the next example is another again important system where, as far as the light weight alloys are concerned, which is magnesium aluminum. So, magnesium aluminum, you see that there is a alpha aluminum solid solution, there is a magnesium solid solution, then you have a beta, you have a gamma, and if you see the one of the example of 4 diffusion couple annealed at 420 degrees for 50 hours. So, this is the schematic, you can refer to this paper for the original micrograph. So, here what you see is you see a gamma and you see a beta phase growing. Okay. So, gamma and beta, again you see here that although the beta is almost like a line compound in this region, but the thickness to which it grows is much more than gamma. So, please do not confuse yourself thinking that here the gamma composition range is wide. So, why is it thin here? The thickness here in the micrograph is not correlated with the phase diagram. What is correlated is the nature of the phases that form. So, now if you try to draw the composition profile, then you will see something like this. So, gamma is a phase which is relatively having a wider composition range. So, here therefore, you see a kind of a gradient, whereas beta is a very narrow stability range, and therefore, it has a constant composition. Now, we see something interesting here, which you may say that sir, is it wrong or something. So, you see that a small amount of gradient is present here, although you see that it is a pure aluminum. So, this is the graph that is reproduced actually from this particular paper. The reason for such deviations can be, remember that this is SEM micrograph which is reproduced here. So, sometimes it may happen that the contrast of solid solution, because the solid solution also has very close to aluminum composition. So, it is aluminum where some magnesium is dissolved. So, the contrast sometime may be not very clear. That may be one reason why we do not see apparently any other phase here. The second could be that the region is thin enough so that you are not able to resolve it very clearly, but when you probably do SEM, TEM or something, it may be visible. Another interesting example is the silver zinc system. So, silver zinc, if you look at the phase diagram, it has intermetallic phases with the wider homogeneity range like beta and epsilon. It also has gamma, and if you see the micrograph of the interdiffusion zone. So, this is between silver and zinc, and you see all these 3 phases form beta, gamma and epsilon. So, all the 3, this is an actual micrograph again which is shown here, and you see that even though here there is a high solid solubility of zinc in silver, this is a very wide region of solid solution, but you do not get any solid solution phases in the diffusion couple. So, it is beta, gamma and epsilon alone. So, that is something again I want to say that we cannot say that whatever the phases are present will all be visible in the diffusion couple. So, if you want to now sketch the composition profile, it looks something like this. So, you see the epsilon phase has a wide homogeneity range, the beta also has a wider range, and the gamma also. So, you have gradients in each of these phases, and then of course, you have zinc and silver as the end members. Okay. Remember, when we also talked about the diffusion couple problem in the solutions to diffusion equations, one assumption was always that the end members remain unaffected. So, in reality, now you can also see that you always have certain regions of the end members or the pure metals which remain unaffected. Let us go to another example. Nickel aluminum is a very important system, especially when it comes to superalloys which are used for high temperature applications. You have different kinds of precipitates that form. So, nickel aluminum, the phase diagram is shown here. This is a schematic phase diagram where you have line compounds like Al3Ni. You have a compound with a wider homogeneity range, aluminum nickel, and then you have Ni3Al. So, here now this shows an example, the diffusion couple which is formed between these two compositions. So, you see now this composition, you see that this is not a pure nickel and pure aluminum example. This is an alloy of nickel and aluminum. This is another alloy of nickel and aluminum, and this is present on both sides of Ni3Al. Such a diffusion couple is called as an incremental diffusion couple. So, this is known as incremental diffusion couple. And now, if we see the how we draw the composition profile, so we see that the composition profile looks something like this. So, you have you notice here that it is not the aluminum, or here it is not going to pure nickel or pure aluminum, but it is going to the alloy composition, and Ni3Al has a relatively wider range. So, you see a kind of a gradient here. So, such diffusion couples are known as incremental diffusion couple. The purpose is that by forming such a diffusion couple, you want to understand the growth of one particular intermetallic. So, that is how we come to this diffusion couple. So, if I want to study only the growth of Ni3Al, I can choose such a diffusion couple, and then so that I am more likely to form only Ni3Al in this interdiffusion zone. So, then another example is niobium silicon, and niobium silicon, here you see a very limited solid solution that is there, and this is a example or a schematic of diffusion couple annealed at 1250 degree centigrade for 24 hours. You notice here again that the intermetallic phase, although both are very close to the line compounds, but you see one of the phases grows substantially than the other phase. So, that is again to say that the thickness of the phases that are developed cannot be correlated to the phase diagram. It completely depends upon the kinetic of the growth of these phases. So, if you look at the composition profile now, you will see that here you have pure niobium. So, silicon is 0, then you get a jump where NbSi3 is formed, and then you have a NbSi2 forming. Okay. So, this is how the composition profile look like, and correspondingly, if you see the niobium concentration profile, then it is the reverse. So, then cobalt tin, again this is an important system when it comes to electronic kind of applications. So, cobalt tin phase diagram looks something like this, a fairly large amount of line compounds, and when you have a cobalt tin diffusion couple annealed at 200 degree centigrade for 625 hours, let us see how it looks like. So, there is only cobalt SN3 phase that is forming. And again this shows us that the thickness, the growth decides which phases will grow. And this is an example of a cobalt SN3 couple where cobalt SN2 phase. So, cobalt SN2 phase is somewhere here that grows when you form a diffusion couple of cobalt and cobalt SN3. So, if you try sketching the profile in both these cases, this is pretty straightforward. You have tin 0 here, then you have the tin composition which is corresponding to COSN3, and then to the pure tin. And similarly here, if you sketch the profile, then you have tin 0 here, then COSN2, and then this is the composition corresponding to COSN3. Then you have vanadium silicon system, where the phase diagram is again lot of intermetallic compounds with almost 0 solid solubility on the silicon side. And if a diffusion couple is formed at 1200 degrees centigrade for 16 hours, so you see that you have thin intermetallic regions of V5Si3 and V6Si5, and then V3Si and V6Si5, and you have a slightly wider zone of V5Si3. So, here 3 different intermetallic phases form, and the fourth one is a large of region of VSI2. So, it again tells us that although there are several intermetallic phases that exist in the phase diagram, one of them grows predominantly here. So, this is slightly magnified view of the same, and by now you must be comfortably drawing the composition profile, that here, because all these are line compounds, so you will see the horizontal run. Remember one more thing, that when let us say in exam or in questions when you are asked to draw this profile, okay, this should correlate with the micrograph. That means, if here VSI2 you see a large region, here also VSI2 should have a larger length. Similarly, here if V6Si5 is small, here also it should be small. So, there should be a correspondence between the thickness presented in this graph versus thickness presented here. Okay. Then as I said, that the thickness does not have correlation with the phase diagram, but when you draw the composition profile, then there should be a correspondence here. We are not asking for exact correlation, but suppose if somebody draws a VSI2 very thin line, in this case it would be wrong. So, moving ahead, so again for the original micrographs you can refer to this paper. Then another example is from molybdenum silicon phase diagram here, where you see again several intermetallics forming. One thing you might have noticed already, that when you have a lot of intermetallics in the system, the growth of solid solution phases is not so prevalent. Okay. So, molybdenum silicon diffusion couple annealed at 1300 degrees centigrade for 16 hours. So, you see a very thin layer of MO5Si3 and a very large section of MOSI2. And similarly, you see the phase diagram, the composition profile here. So, this large region corresponds to the MOSI2, and the very thin region corresponds to MO5Si3, which also has a slight gradient present due to a little bit of range in which it is stable. Now, the last couple of examples are from what are known as multi-component diffusion couple. So far we saw the examples of binary diffusion couples, in which we know that only the single phase regions grow. So, now this is an example of recently developed class of alloys called high entropy alloys or multi-component alloys. And when you have 4 different elements in one alloy, then how do you form the diffusion couple to derive anything meaningful out of it? So, what you do is, so that means for the mathematical analysis. So, one of the approach to do this diffusion behavior in this multi-component alloys is to use what is known as a pseudo binary approach. So, this you see here why it is called pseudo binary. If you carefully see the system here, it is chromium 25, iron 25, these are the atomic percentages, but this is cobalt 20 and nickel 30. Whereas in the other end member, it is chromium 25, iron 25, cobalt 30 and nickel 20. So, when you form such a diffusion couple, then you see that the concentration gradient exists only between cobalt and nickel. Chromium and iron on both the sides are equal. So, if you form a diffusion couple like this, interestingly in this particular diffusion couple, even though it is a 4-component system, but because this alloy system has a wide single phase region, you see only a solid solution phase developed. In fact, in the SEM micrograph you cannot even make out. This is reproduced from a paper, again it was from our research group, but if you see the composition profile, it is difficult to sketch, to be honest, because the contrast is not so clear here. So, I will show you directly how the composition profile looked like. This was reproduced from the paper, and you see here that this is a nickel concentration profile. This is a cobalt concentration profile, because nickel is decreasing from here to here, cobalt is decreasing from here to here, and chromium and iron are constant because there was no gradient for them present. So, you see that although these are 4-component alloy system, but here it is 2 elements only which are actually diffusing. These 2 elements, the concentration gradients are not there. Another way of doing is this diffusion couple in multi-component alloy is not to go for the pseudo binary, but straight away go for let us say here in this case cobalt, chromium, iron, nickel and aluminum diffusion couple. So, here now it is not a pseudo binary case. The objective many times is to understand what are the phases that will form in the interdiffusion zone. So, you see here this is a aluminum fill, and here there is a high entropy alloy. So, you can see already a complex interdiffusion zone developing. You have a region which is lamella like structure, then you have a transition zone, you have oxide influenced region, then you have a Al5 CO2 type of phase. So, based on this the composition is obtained like this. So, here this is the composition that is obtained, and you can refer to this paper further. So, here Al5 CO2, you can again see that you have a single phase region which is Al5 CO2 is not a very wide phase, wide composition phase. So, you will get almost a horizontal line. Plus in this region, which is a lamella like structure region, you see this wavy type of composition profile, which indicates that it is a phase mixture. Same thing for the TZ also. So, these are several examples that we saw today. You are free to refer to many more such diffusion couple examples. See if you can draw the composition profiles, if you can correlate the composition profiles. If there are any questions, please feel free to put in the forum. So, with that we will end this lecture, and next week we will go further ahead from here. Thank you.